Hello everyone, let's take a look how we can approach this problem limit as x approaches 0 from the right of sine of x over x raised to the 6 over x. So we always first ask ourselves, is it in an indeterminate form? And if you really think about the numerator, 6 over x squared, we know the shape of 6 over x squared looks something like this. If you just roughly sketch it, and we're saying approaching 0 from the right, so if we approach 0 from the right, it looks like it's going through infinity. Also, if you really look at sine of x over x, and it really looks something like this, and it's passing through this point 0, 1. So you have it in the form of 1 raised to the infinity. And in class we talked about what are the special forms of indeterminate. So what we really ask next is, what is really creating the problem? And if you really look at it, the exponent being infinity is the problem. And in order to solve this problem, what we usually do is say let y equals all of this. So y equals limit as x approaches 0 from the right of sine of x all over x raised to the 6 over x squared. And why do we do this is because now it looks like an equation, so we can map our natural log functions. And you might say, why do we have to map natural log functions? Because of the fact whenever you have an exponent, the natural log, what it does is you're allowed to sneak the exponent out in front due to properties of natural logarithm. So that's the only reason we do natural log mapping of natural log functions. So we have natural log of y equals limit as x approaches 0 from the right of natural log of sine of x all over x, and if you sneak the exponent out in front, it really looks like 6 over x squared. And now if you really look at it, why are we doing all of this is really the reason behind it is you need to make it look like f of x all over g of x, because L'Hopital's rule can be only applied when you have in the form of a rational expression. So that's why this is really not in the form of a rational expression, because the relationship between 6 over x squared is times natural log of sine of x over x. So what we do on the next step is we usually rewrite so we can use L'Hopital's. So natural log of y equals limit as x approaches 0 from the right. 6 is just a scalar multiple, so we're allowed to just leave the 6 outside, but do not forget to, towards the very end, times it by that multiple of 6. So we have natural log of sine of x all over x, that's the argument of natural log, divided by x squared. It just went in here, but please do not multiply this x squared with this x, because x squared is separated and this x is coming from the argument of natural log of x. Now let's see, we haven't used L'Hopital's yet. All of these are algebras, so we can get to use L'Hopital's. The only reason we're really working with all of this so we can use L'Hopital's, so good news, we rewrote it and we made it in the form of a rational expression, something over something. But you're not really allowed to use L'Hopital's yet, because L'Hopital's can be only used in the form when it's in indeterminate form, in other words. And now if you really inspect the numerator, we know sine of x over x as limit as x approaches 0 from the right. This is 1, so natural log of 1 gives you really 0. Right, so right here this is just 0 over 1 over x. Imagine 1 over x squared at limit as x approaches 0, it's really infinity. So you have in the form 0 times infinity, and those are also one of those special cases. So now yes, we're allowed to use L'Hopital's. So here's my L'Hopital's rule step. So we have, we're using L'Hopital's. So we can write this question again, limit our natural log of y equals limit as x approaches 0 from the right. 6 is just a constant, and if we really think of using L'Hopital's here, we know the derivative of the denominator and we know the derivative of sine of x, right? But If you really think about it, I'm not going to use L'Hopital's. Let me step back a second because it might really confuse a lot of us doing this with a quotient rule inside, because natural log of anything is 1 over that anything times du, and we have to use like quotient rule. So I'm going to step back and I'm not going to use L'Hopital's here. You could have, just I don't want to make it a really long problem because quotient rule can really complicate things. So remember, there are properties of also natural logarithm. We can do is rewrite this as saying natural log of sine of x minus, because division means minus when we talk in the sense of natural log. So I haven't still used my L'Hopital's. All I did is my algebra, because the properties of natural logarithm tells you if you have natural log of x over y, you're allowed to write natural log of x minus natural log of y. Alright, so that's all we used here. We haven't done L'Hopital's. The only reason we didn't do it because we don't want to deal with quotient rule, or I don't want to do with quotient rule and so on. Now let's go ahead and use the L'Hopital's rule that we saved it from last step. So we have natural log of y equals limit as x approaches 0 from the right 6, and here's the derivative of the denominator of x squared is 2x, and the derivative of natural log of sine of x is, we can write them as saying 1 over sine of x times cosine of x due to the chain rule, and the derivative of natural log of x is 1 over x. Okay, so let's take a look what really happens here. So we have natural log of y equals limit as x approaches 0 from the right of 6 times cosine x over sine of x minus 1 over x all over 2x. Let's go ahead and try to clean out the top, the numerator, so we can do our LCD and so on. So we have natural log of y equals limit as x approaches 0 from the right 6 times okay, so the LCD for the numerator is x sine of x. I already have a sine of x, so it will be x cosine of x minus we need a sine of x because you already have a x, and the LCD sine of x times x, so I would write sine of x. If we also rewrite this problem and clean it up, it will really look like natural log of y equals limit as x approaches 0 from the right 6 multiple times, imagine a 1 underneath that 2x. Whenever you're dividing by a fraction, you multiply by its reciprocal, so this would really look like x cosine of x minus sine of x all over 2x gets times with this right here of this complex fraction 2x squared sine of x. Now you might say, why are we doing this? Because so that we can evaluate it, it doesn't look complicated, and if it does not work, we can use L'Hopital's one more time. And if you approach 0 from the right of sine of 0, we know it's already 0 right here on the denominator, so looks like we happen to use also this would be zeros, so we have to use also L'Hopital's on this step. That's why we rewrote it. So if we use L'Hopital's one more time, we get natural log of y equals limit as x approaches 0 from the right 6 times. Okay, so if we really, I might need more space. I will squeeze things in here. Okay, if you use the product rule, because x is timesing with cosine of x, the derivative of x is 1, so I would just have, and let's go ahead and distribute the 6 throughout as well. So if we do that, we're going to have 6 times 1 is 6, so I'm going to save some space, that's why. So I would do 6 cosine of x. Then the derivative of cosine of x is negative sine of x, and you still have that 6x, so you'd have negative 6x sine of x. That's the derivative of this. You don't have to use the product rule here, so the derivative of sine of x is just cosine of x. Do not forget that 6. I'm just throwing in all of those 6 right now, all over. Remember, we don't use quotient rule here. You're taking the derivative of the top and the derivative of the bottom. The derivative of the bottom, we also have to use the product rule. The derivative of 2x squared is 4x times sine of x, f prime g. And the derivative of sine of x is just cosine of x. So you'd have 2x squared cosine of x, g prime f. This is g prime and f. Okay, so let's see where we stand now. Before I do anything, it looks like this and this are like terms, and we get to cancel them. And from the bottom, really looks like I can factor out a 2x. So let's go ahead and do that first. So you'd have natural log of y equals limit as x approaches 0 from the right of the quantity negative 6 x sine of x all over. If I happen to factor out a 2x from the bottom, you are going to have 2 sine of x plus cosine or x cosine of x. And looks like we can also simplify things. So 2 goes into 6 3 times. So let's see what we can do now. We happen to have natural log of y equals limit as x approaches 0 from the right of negative 3 sine of x all over 2 sine of x plus x cosine of x. Let's try to simplify things. If you plug in 0 from the right, on the top you already see what's going to happen. And on the bottom you already see this is what's going to happen, right? But still there might be good news. But this x multiplying with cosine of x as x approaches 0 from the right, this is just 1, but that 0 over here creates a problem, right? So you have it in the form of like 0 over 0. So what do we do? You could have used L'Hopital's one more time, but I'm going to use a trick here. So the trick is, if you recall what squeeze theorem tells you, or the sandwich theorem, if you can have the argument and the denominator the same, and when it's approaching 0, or it doesn't have to be always 0, you can manipulate it, you can say that value is really 1. So I had to edit the video, it was too long, so that's why we're timesing it by 1 over x, because so that we can use our squeeze or the sandwich theorem. And if you distribute the 1 over x to sine of x over x, that goes to 1, and you do the same thing on the bottom. That's 2 plus 1, that's 3. Negative 3 over 3 simplifies to negative 1, but you're really not solving for natural log of y equals negative 1, so that's why we map e on both sides. So we have y equals e to the negative 1. Hope this helps. Thank you very much for watching. Don't forget to subscribe.